Welcome to CSC 321 Operating Systems lecture series. In this segment, we'll be discussing Chapter 4, Threads and Concurrency. In threads, we'll be looking at issues related to threads, how they are created, what are the characteristics of threads, and so on. And in concurrency, we'll see how concurrent programs or jobs can be executed. Let's see what we have next. Outline. In the outline, we have overview and then multi-core programming, which means we are going to design program that can work in a multi-core system or multi-core processors. Then multi-threading model, which means we will be designing or we will be looking at models where multi-threading is available. And then thread libraries. What are the libraries that are available for creating threads? Implicit threading, what it means? Implicit threading is, as we all know, that as the program grows, number of threads also increases. So it becomes hard for the programmer to manage threads. Instead, threads can be created during runtime by the compiler or other programs. So this is called implicit threading. And then threading issues. Issues related to threading will be discussed here. And the last part, operating system examples. We'll see how operating systems handle threads. Let's see what we have in the next. Objectives. Identify the basic components of threads, which means we'll be looking at components that is required to create a threads or associated with thread. And then we'll be contrast threads and process. So we'll be comparing threads and process. We should know that they are really interlinked. Now, describe the benefits and challenges of designing multi-threaded application. Why do we want to design multi-threaded application? What benefit it can give us? Illustrate different approaches to implicit threading, including thread pools, fork join, and so on. As I have discussed in the previous slide, that implicit threading means designing or building threads during runtime. So there are methods of doing that. We'll be looking at that. Describe how the Windows and Linux operating system represents thread, which suggests that these operating systems have their own ways of representing threads. Designing multi-threaded application using pthreads, Java, Windows threading APIs. So these are the objectives of this chapter. So what would be the motivation? We all know that most modern applications are multi-threaded. Threads run within an application. So when there is an application, there will be threads. Multiple tasks with the application can multiple tasks within the application can be implemented by separate threads. For example, update display, fetch data, spell checking, answer a network request. So these issues we can see these we can if I select a color, uh, these are examples of threads. Let's say different threads are assigned for this work. That means one thread is updating display, one thread is fetching data, one thread is for spell check, and then network request. Where can we see that? A very common example is when we work with, let's say, Microsoft Word. We keep on composing, but we can also see that the spell checking are underlined. How this is possible? This is possible because multiple threads are working at the same time. They have different responsibilities and they are performing their job. That's why even when we are composing, spell checking is automatically done in the background. So this is what multi-threading application is. Now, process creation is heavyweight while thread creation is lightweight. In the next slide, we'll see what this line means. But just for the time being, remember that creating a process requires more resources, but thread requires less resource. Can simplify code and increase efficiency. Code can be really simplified and it can improve the program's efficiency when we implement multi-threading operations. And kernels are generally multi-threading. That means there are multiple threads working inside the kernel or running inside the kernel. As I said that we'll see why process is heavyweight and threads are lightweight. Now let's say a process has one thread like this one, this process has one thread. Now see the help that this process or the resource that this process requires: register, program counter, and stack. And then this is your code, and then data space, and your files. So when we create a process, for every request we need to have registers, program counter, and stack. But if we look here, see, these are different threads. See what they need. They are sharing the resources of the process that this thread belongs, because this is resources required by a process, but this thread is under that process, which means this thread, when we are working with this thread does not require any extra resources. It works with the resources that the process has. So this is really beneficial. And remember that when you compare process and threads, process are much slower than compared to threads. Threads are lightweight and they are really fast. See, this is another thread and this belongs to a different process. This is another thread, this belongs to a different process. But even though there are three different threads, they are using the resources assigned to a process. We can have more threads here, we can have more threads here, we can have threads here, we can have threads here, we can have threads here, and so on. No matter how many threads we have inside this box, or let's say this process, let's say this is process P1, this is process P2, and this is process P3. No matter how many threads do we have inside process P1 or P2 or P3, they will be using this resource. No other resources will be required. But when we have another thread like this, then then we need to have register, program counter, and stack. So when you create a new process, we need these resources. But when you create a new thread, existing resources occupied by the process can be used or are used. So these are the differences between a single threaded and multi-threaded process. So let's see what we have in the next slide. Multi-threaded server architecture. You can see in this diagram that the client is requesting some service from the server. If this is single threaded process, if the server is a single threaded process, then what would happen when the server is serving this client, then if it receives other requests from other clients, let's assume this is web server, so this server is bound to get more and more requests. So if this is single threaded process, then until and unless this service is done, all these clients, let's say this is C1, this is C2, this is C3, and so on. These clients, they have to wait. Now, one solution could be that this server may have multiple processes to handle multiple requests. Now, we have seen in the last slide that creating a process is costly because it requires more resources. Now, what we can do is we can create threads. So, if this server is a process, then we could create multiple threads under that process, and that those threads handles these different requests from different clients, which would allow us to make this service much more faster, and it's cost effective as well, because we are not creating threads, which means we are not occupying resources. We are using resources occupied by a single process, but under that process we have multiple threads. Those threads, they are attending different requests coming from the various clients, and they are processing those requests coming from various clients. Let's see what we have in the next slide.